Welcome to the third segment of the week's lecture. In this lecture, we are going to discuss differentiation formulas or differentiation rules, you may think. So far, assume that we have learned the classical definition of the derivative, and now it is very hectic to use or difficult to use to find derivative of some complicated functions. If functions are given in, let's say, product form, 2, 3 or 4 functions are multiplied with each other, and there is some function in the denominator also, the quotient functions, then it will be very difficult to, let's say, apply basic definition to find derivative. So some rules are already defined, and many of these rules you already use, like product rule. So if two functions are given in form of product, you know how to get derivative of those functions, right? You already remember the formula. So these are, let's say, those formulas. So I will just go through very quickly in this presentation, because the mostly things are already known to you in your college mathematics. Start with the before starting formulas or the, let's say, rules. So let's look at this graph of function y is equal to f of x, this one. Okay, just look at it, just skipped, and I wanted to show you the tangents at the point x is equal to 0, there are no tangents. So derivative of polynomial and exponential functions. So when polynomial is constant, for example, it is equal to c, then its derivative is 0, so slope is 0, and derivative on every point on this line is simply the same line, and the slope of this line is 0. You already know that, and you can prove it using this definition, and it is done here, like it is equal to 0. So our rules are basically rules. And now the power of x, and generally when there is an n power, so how do you derive this function or get derivative of this function? So you just bring n as a coefficient, and x you reduce power by 1, n minus 1. So this is derivative of the function. This thing came from the basic definition, and this is what it is proved here. So when there is power 1, it is 1, then power is 2, it's 2x, power 3, it is 3x squared, 4, then 4x cube. So for x is equal to 4, it is proved using basic definition. So this is formula, and generally for power n, so we summarize this power rule as, so this is formula for differentiation of x power n is equal to n x power n minus. This example x power 6, and this is derivative which is equal to 6 x power 5, and you can verify this using basic definition. And even for any power, let's say 1000, so differentiation will be, or derivative will be 1000 times x power 999, like 999, 1000 minus 1. So there must couple of more examples, and this is general version of the power function. So first n was like natural number, any whole number, and now it is real number. For example, x power 1 by 2, which is exactly square root, or x power 3 by 2 negative. So this will also work, this formula will also work, or it is also valid for these fraction numbers. So it's not only true for whole numbers but also for real numbers. Okay. Yeah, new scaling example, 3 can be taken out of the differentiation. You already know about this. This is simple law. And new derivative from old means derivative of f, derivative of g computed separately, or the functions are added, then you find differentiation. So it's the same thing, and this will be true for all functions, similarly for subtraction. And now here comes the exponential function for general number b. So it's not only e but b, and e is simply a special case of e. Now, for example, if b is equal to e, then this limit goes to 0, e power h minus 1 divided by h, and applying L'Hopital rule. So this complete term will reduce to 1. So this will be e power x times as a special case. So e power x. Exponential function, this is how it is proved, this identity from here using L'Hopital rule. And this is exponential function finalized, example about exponential functions, and I think this is the last one. That's it. Thank you very much. See you in the next slide.